Hello. So in this video I want to talk about the advantages of 3D printing and how it can potentially help blind and visually impaired students understand chemistry concepts. So I'm going to show you all the models which I created one by one and show you what I tried to do to help these blind students. So first I'm going to start with my water molecule. So as you can see with this water molecule, I tried to represent the two hydrogen atoms as these two little ones bonded out from this big large central atom representing the oxygen atom. And then you can see these two pairs of like little bumps, which I like to call protrusions, which will represent the lone pairs. So if a blind student were to fill this model, the three atoms, these two small ones, and this central one, including the bond angles and the two lone pairs, as you can see right here, 1, 2, they could distinguish this molecule as a water molecule. Also, if I were to give them this ammonia molecule right here, they could feel the three hydrogen atoms which are bonded to the central nitrogen atom, plus feel this lone pair right here and distinguish it as an ammonia molecule. To represent a charged molecule, I try to kind of make a minus symbol coming out of a hydroxide ion, which kind of looks like this. So here you could see that the large central atom would be the oxygen, the small one the hydrogen, and then you can see three lone pairs, one right here, one on the top, and one on the bottom. And I tried, as I said before, I tried to represent it being a charged molecule by this little negative sign coming out. So if a blind person were to feel this molecule, they could feel the three lone pairs and understand that it is a charged molecule by feeling this minus sign right here. Okay. And also, I tried to kind of make a benzene model which kind of looks a lot different from what we're used to. And I try to do this because a blind person would understand that single bonds are longer than double bonds. And they probably wouldn't grasp the concept of resonance right away, but by giving them kind of an exaggerated benzene ring, as I would say, and then an accurate benzene ring, they could probably try to understand resonance and why a benzene ring has equal bond lengths all around. So as you can see here, these atoms right here, these 6 atoms represent the carbon atoms, and the little ones will represent the hydrogen atoms. So to bring it closer a little bit, these longer bonds will represent the single bonds, while these shorter ones, the double bonds. You can actually see a little spacing right there, which kind of shows you that there's 2 bonds. So if a blind person were to feel this, they would see how it would alternate with single or double bonds. Now if you were to give them an accurate 3D model of a benzene ring, they can distinguish the difference, and it can potentially help them to understand why and how a benzene ring actually looks the way it is. So another model which I created to show the overlapping of the pi orbitals of a benzene ring is this model right here. I created it kind of small, but as you can see here, let me find an angle where you can see it the best. So as you can see here, the atoms in the central ring represent the carbon atoms, and this model kind of blends in with my shirt, so excuse me for that. But if I maybe tilt it this way and just rotate a little bit right there, that looks like a good model, a good angle actually. So right here, this atom and this atom, and the little ones represent the carbon and hydrogen atoms, and then these dumbbell shapes coming out of the carbon atoms represent the pi orbitals. And I also have a ring connecting all these pi orbitals, showing the overlapping of them, as well as little protrusions, if you can see them, representing the electrons, as you can see that one right there. And if they were to feel this model, they can grasp how pi orbitals actually overlap, and how electrons would flow from one orbital to another, and how this right here is the reason why benzene ring doesn't look like the one that I showed you previously, which was very exaggerated, and why it is resonance stabilized. A last model which I created was a model for organic chemistry representing a mechanism. So here, this will represent an alkyl halide. I represent the carbon chain by these rectangular bonds, and then I represented the halogen, which was connected to the carbon chain, as you can see here, by a more circular, or not circular, but more round bond right here. So if this would react with a hydroxide ion, which I showed you previously, which has 3 lone pairs, and that negative charge on there, then this would result in an SN2 mechanism and convert this alkyl halide into an alcohol, as I showed here. So as you can see, the top one is the alkyl halide, and the bottom one would be the alcohol. So let me put the alkyl halide down for a minute and show you how, with this hydroxide ion, which would react on the carbon that was initially attached to the halogen, how it would result in a bond which is more round, and also it loses one lone pair, which would represent this new bond right here. And also the halogen, which was displaced, would also be felt by blind students, and they would be able to see how it has 4 lone pairs plus its negative charge. And by blind students feeling all these models which I showed you, they can potentially better grasp all the chemistry concepts which they can actually see. So I hope in the future to make more models like this to help students in this condition. And I would like to thank my professor, Dr. Schreck, Dr. Tickner, the Dean of the Honors College, Dr. Dabke, and everybody else who has supported me in this project. Thank you, and I hope you enjoyed this video.